This is Clearance, an air traffic control and air defense training simulator that I built, solo in Unreal Engine. The layer I want to show you today isn't the gameplay, it's actually the network layer underneath. This is the IEEE 1278.1 standard. It lets military training simulators from different vendors share virtual battle space. Every serious defense industry training program runs on it, or its successor, HLA. Clearance implements 6 PDU types across 4 protocol families, with the byte-perfect wire format compliance. As you can see, Wireshark is capturing UDP port 3000 on the loopback adapter. Nothing is on the wire yet, and Wireshark ships a built-in DIS dissector, so that anything Clearance sends, Wireshark is going to pass and label for us. That's the third-party validation on the wire format. So if we tab back in on the project, we click Emit on the DIS Federation panel, you'll now see the emit counter tick straight up. This means that Clearance is now publishing IEEE 1278.1 entity state PDUs for every aircraft, and Emission PDUs for every radar to the multicast group. Real wire format packets, ready for any peer federate to pick up. And so, one click, and Wireshark is now receiving entity state and emission PDUs continuously. Heartbeat traffic, 1 per aircraft per tick, and 1 per radar per tick. Every aircraft in Clearance is a spec-compliant DIS entity. The Wireshark shows IEEE 1278.1A 1998 in the header. The entity type classifies it as an aircraft. Then the entity location is ESEF meters, big endian per the spec. The entity orientation gives the yaw pitch and the roll in radians. And the entity marking field carries the call sign as ASCII, DLH105, BAW472, and whatever's flying at the instant. Any DIS federate on the network can read this and add the aircraft to its own scope. Now, if we change the search filter to Emission PDU, the Emission PDU is what makes Clearance useful to an ELINT or radar warning receiver federate. It broadcasts my radar fingerprint, center frequency, pulse repetition frequency, pulse width, effective radiated power, and the emitter catalog code. 9.5 GHz, 1 kHz PRF, and 1 microsecond pulse. That's how a receiver classifies the radar type. Below that, the track and jam block lists every entity ID that this radar is currently painting. So if you were flying a fighter federate in this exercise, and your entity ID appeared in this list, your warning gear would spike. So if we tab back into the Clearance window again, we'll spawn a hostile bandit in. And we'll scramble GCI to it. And so now if we tab back into the Wireshark and we filter for PDU type 2, fire PDUs, because I just scrambled a 3-ship intercept on a hostile, Wireshark shows 3 fire PDUs, 1 per interceptor, emitted in the same microsecond burst: firing entity, target entity, munition entity, event ID, world location, munition type, velocity, and the range. The whole IEEE 1278.1 section 7.3.3 field set. 96 bytes exactly per the spec. And so if we tab back in on the project, the intercept plays out, the Vipers vector onto the target, and settle into escort formations, and the bandit gets pushed out of the sector. And so once the intercept resolves, and we change over to Wireshark and filter out for PDU type 3, the detonation PDUs, 3 of those detonation PDUs show up. The same firing entity ID, the same target entity ID, the same munition entity ID. The event ID matches the fire PDU, and that's the DIS native way of pairing a weapons event. Fire opens the event, and detonation closes it. The detonation result code 2 entity approximate detonations. It's the standard non-lethal escort out semantic used in air traffic controller and air defense training. Wireshark passes every field, frequency 121.5 MHz, air traffic controller guard channel, bandwidth 25 kHz, VHF airband spacing, amplitude modulation, generic radio system with no encryption. The entity type identifies what this is. Kind 7 means radio, and domain 2 means air, so it's an airborne radio. Transmit state 1, on, but not transmitting. Means that the radio is powered up and tuned, but nobody's speaking on it yet. This is what a Federation receiver uses to know what frequency to tune to before hearing any traffic. So if we now tab back in on the project on the operator side of things, and we instruct in aircraft like Speedbird 159, Speedbird 159, turn right heading 125. So, as you can see, the moment that my instruction actually gets processed, the ground station's transmit state flips to 2, on and transmitting. When the pilot reads back, his aircraft's radio does the exact same. Federation observers see this in real time. They can build a live "who's on the air" radio right now picture from transmitter alone. Paired with transmitter is a signal PDU, type 26. Every voice line the sim produces goes out as raw binary payload, alongside the transmitter announcement. Same radio reference ID so that a receiver can pair them. The transcript is carried as raw binary data, encoding class 1 per the spec. So a Federation observer logs the whole voice picture without ever needing a codec. Look at the hex pane on the right. The ASCII payload is readable directly. Data length in bits plus the padding to a 32-bit boundary follow section 7.7.3 exactly. One more thing worth showing before the test. All the wire format code lives in its own standalone C++ module, ClearanceDIS, completely isolated from the game engine. Public API is pure standard C++, no fname, no fvector, no uobject, no unreal types across the boundary. Just pod structs, standard vector, standard string, and C standard int. The entire public API is one file, ClearanceDISPDU.h. One header, 6 PDU input structs, 11 wire format functions. A deterministic FNV1A cosine hash. That's the entire surface. Presentable to any C++ engineer without a single line of Unreal context. The Unreal side emitter is a thin adapter that converts my game types into these pod types and delegates. This is what the legacy training rigs already run on. But the forward-looking work, face standard avionics, autonomous wingmen, that's all built on DDS, the OMG Data Distribution Service standard. RTI Connext leads the commercial markets. eProsima Fast DDS is the open source C++ implementation. This is what the new defense systems talk on. Clearance publishes the same 6 primitives: aircraft state, fire event, detonation event, radar emission, transmitter state, and the signal event, as DDS topics under a clearance namespace. The types are defined in an OMG DDL, code generated via Fast DDS Gen wire, encoded as a CDR inside RTPS, same architecture as the DIS side, pure C++ standalone module, and a thin Unreal adapter on top. And if we tab back in on the project again, and we find the DDS Federation panel, and we click on emit, you'll see the emit counter tick up. And the same pattern from the DIS Federation if we search up and filter RTPS on the Wireshark. And so as you can see, Wireshark's dissector recognizes the RTPS wire protocol that the Fast DDS runs on. Vendor ID 01OEF, eProsima. Continuous participant discovery on domain 0. When a subscriber matches, the user data flows on all 6 topics. The subscriber running in the same process just received 9,000 plus samples end to end. The publisher writes on the SymTick, the subscriber gets the data via DDS transport, same units, same field mappings as the DIS side. A DIS to DDS bridge is a struct to struct copy. That's the pattern real integrators used to keep a legacy DIS Federation and a modern DDS pipeline in sync. And backing all of this, 14 automation tests across 6 DIS PDU types. Every PDU serializes to a known good byte pattern, passes back to the same struct, and the test failed loudly if any field drifts from the spec. Malformed traffic rejection is under test. Padding boundaries, operator versus aircraft entity routing, empty track and jam lists, transmit state round trip, and every edge case the spec calls out is pinned. This is how you'd catch a regression before it hits an integration exercise. And so as you can see, 14 success results. eProsima Fast DDS is the open source implementation. but what defense primes actually deploy on is RTI Connext, the commercial DDS market leader. So I ran the same 6 topics on both runtimes simultaneously. And so again, same pattern, we click on emit and we see the counter tick up. And this is RTI's own administration console, the same level tool their engineers use to introspect production Connext deployments. It discovered my clearance process automatically, drew the whole entity graph, and stamped it as a vendor 0101 real-time innovation Connext DDS. That's their commercial runtime confirming that this is a legitimate Connext application, not a mock. 6 topics, 6 writers, best effort QoS, same 6 data primitives as the DIS side and the Fast DDS side. And this is the unfakeable one. You can screenshot code all day, but only a real Connext runtime with a valid RTI license populates this window. And if we return to Wireshark and we filter out for RTPS, you'll now see 2 different vendor IDs. 01OEF is eProsima Fast DDS, and 0101 is RTI Connext. 2 independent DDS runtimes, both Y compatible with the OMG RTPS spec, publishing the same 6 data primitives from the same authoritative game state on the same tick. And that's the pattern real integrators would use to run a mixed Connext or Fast DDS federation. Separate domains for discovery isolation, common IDL, and a common wire format. And then we have the final standard, which is one that I've been mentioning throughout, the HLA, High Level Architecture, IEEE 1516-2010. This is what NATO federated exercises actually run on, what the MOD training programs phases federates over, and what most legacy DoD training rigs still use in 2026. And unlike DDS, HLA doesn't have a shipped visualization tool that works on open source runtimes, so I actually wrote one. OpenRTI is the open source IEEE 1516-2010 RTI. It ships an RTI node executable that federates connect to. I built it from source, vendored the binaries under the plugin's third-party directory. Double click, and it's now listening on TCP port 14321, silent by design, same as a database server on a production simulator rack. And if we head back into the project again, you'll see the HLA Federation panel. And as you might be expecting with the same pattern with the other Federation panels, it's a simple click to join. And you'll see the UDP counter tick up. So, one button joins the Federation execution. Clearance registers as the clearance instructor federate, passes my extension from XML, resolves object class and attribute handles, declares publication, and starts pushing attribute updates on every aircraft in the sim to the RTI. As you can see, the updates total is climbing. That's every update attribution value call that the RTI ambassador accepted. The Federation object model is authored as a standards-compliant IEEE 1516-2010 FOM Module XML. It extends CSOR RPR-FOM 2.0, which is the same reference FOM every real defense integrator uses, with an ATC managed aircraft subclass, squawk code, flight phase, active clearance text, and a controlling facility. And crucially, each attribute declares its own transport QoS. And that's ultimately best effort for the volatile state fields, reliable for the clearance text. That declaration is what the RTI enforces on the wire. This XML would pass in any conforming RTI, pitch PRTI, mock RTI, RTI prime, OpenRTI, and any other federate could subscribe to it. HLA, however, doesn't ship a runtime visualization tool the way that DDS vendors do. There's no equivalent of RTI's admin console for OpenRTI. There's no Wireshark dissector for HLA because the wire protocol between federates and the RTI is implementation specific. So I actually wrote my own. This is Clearance HLA subscriber, a completely separate process, a second federate joining the same federation from the same C++ codebase. It subscribes to the 8C managed aircraft and prints every attribute update it receives. It fully publishes everything, the RTI subscribe round trip on a live federation, proved from my own code, nothing paid and nothing black box. Active clearance and ATC facility of HLA reliable. they batch into a separate reflection call. The RTI respects the per attribute QoS the FOM declared, delivers them as separate updates. If you stripped the transport declarations and made everything HLA reliable, these rows would merge. This is the HLA runtime model working end-to-end from XML declaration to live behavior. And so, to conclude Clearance's backend network architecture, it speaks 4 interoperability wires: IEEE 1278.1 DIS, OMG DDS via eProsima, Fast DDS and RTI Connext, and IEEE 15/16/2010 HLA via OpenRTI. The same 6 data primitives on all 4. The same authoritative game state feeding all 4. Every federate the demo just showed was code that I wrote: publisher, subscriber, adapter, and FOM. But you might be wondering, what does the front end of this architecture actually look like? So let's get right to that. So far, everything you've seen has run in one clearance process. Here's what happens when we run 2, each one server authoritative over its own sector, sharing a picture through the federation wires. Two processes, 2 site IDs, federation identity has to be unique per federate, same as the DIS spec calls out in simulation management family. Both wires up on both federates. DIS emitting to the standard multicast group 224.0.0.1 and DDS on default domain 0, no config files, no hand editing INIs, just click some simple buttons. Both federates are emitting and receiving simultaneously. Wireshark confirms the bidirectional flow. Notice the source column bouncing between the 2 ports the federates process bound. Different PIDs, different sockets, all traffic goes over the loopback multicast group. There's no in-process shortcut being taken. So the left federate spawns in Emirates 198. Notice the own chip on the aircraft row identifying it as a locally authored aircraft. And on the right scope, the same aircraft appears within a tick, but with a Site 1 chip. That chip is what tells the right side operator this is a peer-owned aircraft. The row exposes read-only fields. If I try to reclassify it on the right, nothing happens. The ownership check on the receiver rejects any state overwrite for aircraft the local federate doesn't own. The same doctrine as real ATC handoff. Each facility has authority over its own sector's aircraft. Peers, just see the picture. And if we stop emitting and stop receiving with DIS, and we clear the sectors, and we turn DDS Federation on, as you can see, the same result. And now for Emirates 201, if we classify it as a hostile on this instance. So as you saw on the left federate, I reclassified the Emirates aircraft as hostile. And on the right federate, in real time, the aircraft symbol turns red. That's not just position and velocity crossing the wire, it's the full ATC picture, true affiliation, force ID, active emergency, emergency timer, squawk code, flight phase, all federated in the DDS aircraft state topic. A pure DIS entity state PDU can't carry any of that. And so that's it. 1 sim, 4 wire formats, real DIS, real DDS, real Connext, and real HLA. Interoperability that isn't a screenshot. If you want to see what flies the aircrafts, Simulink autopilot link below. If you want to see what detects them, Simulink radar right next to it. Thank you for watching.